Okay, so we started the weak acid equilibrium stuff in class on Tuesday. So now we're going to get into weak bases. And what you're going to find is that the weak bases literally behave the same way, but now instead of just focusing on the hydrogen ion concentration, now we're going to be focusing on the hydroxide ion concentration in relation to the hydrogen ion concentration. If you look at this example here, what you'll note is that the base, NH3, has a conjugate acid, NH4+, that once the reaction occurs and I look at the reactant side, what I'm doing is trying to discern what will behave as the base, what will behave as the acid. In this example, you can see that NH3 here, it will pick up a hydrogen on the product side. So what this means is that NH3 is accepting a proton. It's accepting a hydrogen. That hydrogen is coming from water. We know this to be true because what was H2O is now OH on the product side. That means that water lost or donated a hydrogen. So the NH3 is behaving as a base, and water, which is amphiprotic, meaning can behave like an acid or a base, is behaving as an acid in this particular situation. So today in class, we had Kas. Kas equal products taken to the power of the coefficient over reactants taken to the power of their coefficient, and those coefficients are from the balanced chemical equation. Kb is the exact same formula. Note, we don't talk about water because it is a liquid. We do not count liquids or solids. Those are not counted in the K equation. So far up to date, we have had a Kc, constant with concentration, a Kp, constant with pressure, a Ka, constant with weak acids in water, and Kb, weak bases in water. Okay, so Kb is the dissociation constant of the base, ergo the B. That's why we talked about Ka being the acid dissociation constant. Kb, we can find those values on a chart just like any other Ks. There are generic charts that have to do with Kas and Kbs. I will upload Ka and Kb lists of the most common ones that will be useful for you when you're doing homework. Again, the same rule applies. The Kb value that is closest to 1 means it's a stronger base. These Kas and Kbs are going to become very important when we're trying to decide which reaction is favored, the forward or the reverse. If your Ka in a weak acid reaction is very high in, let's say, the product side, then the forward reaction is favored. The same is true for Kb. Wherever the Kb is with the highest value, that reaction, forward or reverse, is what is favored. So we can see here I've circled ammonia's Kb value and the hypochlorite ion value. We can clearly see that the Kb for the ammonia compound is much higher than for hypochlorite. So that means this one is winner, winner, chicken dinner. it is the much stronger base. So we did this in class today. The same format is going to be followed, except now we're just dealing with bases. So there's a couple of little different add-ons we have to put in there. Just like we said before, you got to know the basic fundamental structure of weak base with water is going to give you the base anion or conjugate acid and the hydroxide anion. Just like with weak acids, we had some weak acid plus water is going to give us the anion of the acid plus the H3O plus. In this case now, we are just simply using the hydroxide ion and the NH4 plus. So if we know that we have a certain molarity of NH3, now we're going to find the pH. So this is a pH, finding the pH of a basic solution given a Ka and a molarity of the weak base. The first example we did in class today was you were given a pH of a weak acid and asked to find the Ka. Now, the second example we did in class was the reverse of that. This is also a reverse of the first example we did on this. So you're given a molarity, which is always the initial solution of the weak base, and we're going to have to go through all those steps to find the pH. We know that it's products over reactants, Water is ignored because it's a liquid. Liquids and solids we ignore. And we were told, or we are told in this example, that 1.8 times 10 to the minus 5 is the value of Kb. Okay, remember, if A equals B equals C, then by definition, A equals C. So what we have immediately to think about is ice table. We were told, find the pH, you have a molarity, you have a Kb. So we're going to do our ice table. Looks a little bit funny than what we're used to, but that's okay because this is a little bit simpler information. We know we started out with 0.15 molar. That comes right from the chemical equation, or from the given information in the problem. We know we initially have nothing of NH4 plus and nothing of the hydroxide ion. So at equilibrium, we're going to have 0.15. Now, I don't like that these slides do this because we're actually going to have a numerical value based on what we calculate here. But again, this is under the x is small approximation, which again means if I'm on my digital scale holding a penny and I put my penny down, the number on the digital scale is really not going to change. The value of the change is so insignificant for the starting point that if I were a Weight Watchers member, I wouldn't even know I lost that 0.005 pounds, for example. Okay? So how do we figure this out? We have to first figure out the hydroxide ion concentration. These are basic solutions. So when we do the math and we find the change, X, it's going to be finding it for hydroxide. So we set it up. 1.8 times 10 to the minus 5 equals x squared over 0.15. Again, x is small approximation. So if we had originally had 1.8 times 10 to the minus 5 equals x squared over 0.15 minus x, we would say, okay, x is small approximation. We're going to pretend that doesn't exist. And now we're going to deal with just the 0.15. Okay? Remember that x is small approximation. We always have to go back and check, and I'll do an example of that in class when we work problems. But the x is small approximation is what we're using here. So when I do the math, I hit the wrong button, sorry guys. When I do the math and I solve for x, I'm going to multiply by 0.15 to this side to make it cancel. I'm going to do the same thing here because if I do it to one side, I have to do it to the other. So what I'm left with is 1.8 times 10 to the minus 5 times 0.15 equals x squared. So now I'm going to take the square root of both sides to get x by itself, and I'm left with 1.6 times 10 to the minus 3. So what does this really mean? What this really means is the value of x is the change that occurs. Because products are being produced from 0, the change is also equal to the concentration at equilibrium. So that means I have 1.6 times 10 to the minus 3 equals x. So the concentration of hydroxide ions and NH4 plus ions is both 1.6 times 10 to the minus 3 at equilibrium. Remember, if there had been a 2 coefficient in front of the hydroxide, just for example, then the hydroxide ion concentration would be 2 times 1.6 times 10 to the minus 3 because it would have actually changed by 2x. So now we know the hydroxide ion concentration. It is equal to 1.6 times 10 to the minus 3. To find the pOH is the same mathematically as finding the pH, except now we're taking the negative log of the hydrogen ion concentration, which is 2.80 in this case. So in your calculator, you would say negative log times 1.6 times 10 to the minus 3, hit enter, and you would get 2.80. To find the pH, remember, pH plus pOH equals 14. That was another formula I gave you last week. So we're going to say 14 minus 2.80 gives us a pH of 11.20. This should make sense because this is a basic value of pH. 11.20 on the pH scale indicates something is basic. And we are talking right now about weak basic solutions.